Sí, bueno, no, sin problema.
Sí. Ok, entonces, muy bien. Buenas tardes a todos. Bienvenidos al coloquio semanal del Instituto de Ciencias Físicas de la UNAM en Cuernavaca, en México. Nuestro invitado hoy es el doctor Adolfo Grushin. Y déjeme decir algunas pocas palabras sobre su vida. Adolfo hizo su doctorado en 2013 en la Universidad Autónoma de Madrid y realizó después un postdoc en el Instituto Max Planck para sistemas complejos en Dresden y después una estancia postdoctoral en la Universidad de California en Berkeley y en la Universidad de Oxford. Desde el 2017, él es investigador en el Institut Niel en Grenoble, en Francia. Y es autor de más de 70 publicaciones, incluyendo 2 artículos en Nature y 8 en PRL. Y esos trabajos en total recibieron hasta el momento aproximadamente 5.000 citas. Sus intereses de investigaciones se centran en la teoría de la materia topológica y en particular en aislantes topológicos amorfos. Adolfo, muchas gracias por aceptar nuestra invitación hoy y esperamos a tu conferencia. La conferencia va a estar en inglés, pero preguntas están bienvenidas en inglés tanto como en español.
Sí, voy a cambiar a inglés más que nada porque estoy tan acostumbrado a dar esta charla, bueno, no esta específicamente porque esta la he preparado para esta ocasión, pero más o menos la temática en general, así que voy a pasar a inglés, pero bueno, sí, más que nada para no trabarme al encontrar las palabras que no sé. Y si hay alguna pregunta en español, pues no, obviamente no hay ningún problema. Okay, so I'm switching to English now. I'm gonna move this window somewhere where I don't see it too much. And yeah, so I'm gonna tell you a little bit about amorphous topological solids, which is kind of a new direction I'm taking within the field of topological phases of matter. And there's always students or postdocs or people that are not in the field. So I want to start like relatively basic and kind of build it up to more kind of concretely what we are doing. But I don't have to get to the end. So if there are any questions at any time, please feel free to interrupt me. Right. So what are topological insulators? So just broadly speaking, there's they're in between insulators and metals. So it's like a very annoying present to unwrap. It's something that is insulator in the bulk and it has conducting surfaces it has conducting surfaces or conducting edges in 2D, and the feature is that they cannot be removed. They're not accidental. They're really robust and actually protected. So, in fact, one reason you should care about topological solids is because actually more than half of the materials we know exist are predicted to be topological solids, at least at the Fermi level. Even if you count bands that are not at the Fermi level, that's even the percentage even goes higher. And what this means is that these materials are, as I say, insulating in the bulk, and in the surface, if we look at how electrons disperse, they have this dispersion relation that looks like a cone or a Dirac cone, and it means that it's gapless, and that means that it's metallic. And they come in many varieties. Some have conduction only at the hinges where 2 faces meet. Sometimes you get states at the corners, but nonetheless, the general idea is always the same. There's some insulating bulk and some conducting surface or edges. And so how do we find them? Now actually it's relatively easy for a theorist, at least like I am, to go online and actually click on the elements that your favorite experimental friend is growing and for example, bismuth and selenium here. And you will get in this databases, you'll get some numbers. And these numbers are actually what we call topological invariants. So there are numbers that characterize these phases and tell you whether or not you'll find these topological edge states or surface states at the surface of your material, and what kind of surfaces do you, surface states do you have. Now, this topological invariant sounds a bit mysterious, but what it is a way of extracting information from the wave function of a material. You take some integral that involves all k momenta, and you get a number. And this is kind of generically what a topological invariant is. And the claim is that this number won't change so long as you're in a given topological phase. And that's what makes it robust, and that's what gives it the name of topological insulators. And what's physically important is that these invariants actually tell you that certain responses, for example, if you shine light or you measure some transverse current, will be quantized in units of fundamental constants. And that's independent of the material you're looking at. However, actually, in practical terms, this is actually quite hard to calculate and numerically costly, at least theoretically, to calculate this topological invariant. So people have, as we often do in physics, use symmetries to simplify these calculations. You already saw actually one symmetry here, which is translations. So if I can label my states in momentum, I am implicitly using translational symmetry. But people went actually kind of far beyond that and took more symmetries of the space group, which means like all the lattice symmetries like translations, rotations, etc. And now if you give me the space group, you give me the orbitals you want to put in this space group, which means just the crystalline lattice. And where these orbitals are in real space, what you will draw is this band structure, but not only that, you can assign little labels to certain points in momentum. For example, let's say 0 and pi, for example. And these pluses and minuses are just eigenvalues of the symmetries, because I can diagonalize this, the Hamiltonian at the same time as this operator. And so I can label not only my states with k, but also with some pluses or minuses. And how these enter the calculation of topological invariant? Well, instead of actually having to know everything that happens with the wave function in all momenta, you can actually just take the specific points like 0 or pi, like what we call high symmetry momenta, and multiply literally this eigenvalues of the symmetries. In this case, for example, inversion eigenvalues in the time reversal invariant momenta. So it just means kind of special momenta in the Briand zone that transform nicely with respect to the symmetries of the system. And you'll get, in this case, in the case of inversion, you'll get either a plus or a -1, and that's your topological invariant, essentially. If you get +1, then it's a trivial insulator, no surface states, nothing special happening. If you get -1, then you will get something non-trivial. So, as I say, this has been pretty efficient in finding how many topological insulators and metals actually we have. And but of course, when you have something nice, you want to see how robust it is. And kind of the nice thing about topological insulators is that if you add disorder, they are robust. And not only that, you can actually induce topological phases with disorder. So this is something that I'll touch upon in my talk. But for the moment, let me just highlight some choices you would have to choose a disorder. For example, you have bond disorders, meaning like the hopping amplitudes of this electrons hopping in a lattice will be just randomly selected from a distribution. Then you have on-site disorders, so the on-site energies are kind of maybe there's some different potentials at different sites. This is the typical disorder. And what's also possible is that not only like all the hoppings and all the on-site energies can be the same, but the connectivity of the lattice is different. For example, here you see hexagons, but here now you have some pentagon, or you have some other types of polygons. And turns out this is also quite important, is actually quite the central topic of my talk. And in fact, just as a 0th order definition of an amorphous material is all of these disorders appear at the same time. And that means that there's no translational invariance, there's no long range order, and also the energy scales are kind of fluctuating in space. Now, what's interesting is that already people in 2009, they realized that, for example, on-site disorder acting on a crystal can lead to get you from a trivial insulator to a topological insulator. And the way it works is that you start, imagine you're plotting the bands as a function of energy, and I park my Fermi energy here. And then as I tune this order, which is this W, you suddenly inverted the gap. And these, what you have to imagine is that the symmetry eigenvalues kind of change if you want, and the gap is inverted. And in what this means is that you enter a phase that is a topological insulator, or a topological Anderson insulator, because it's induced by disorder. Of course, if disorder is very, very strong, then at the end you will still recover an Anderson insulator. So meaning that the electrons, if the disorder is infinitely strong, they will localize. They will never know that a topological phase ever existed. But nonetheless, this just to say that disorder not only can be an enemy, it can also be a friend in terms of realizing topological phases. And people actually started getting creative. So I mentioned this is disorder in a periodic system, but you can also find non-crystalline examples of topological phases, like, for example, quasi-crystals. Here I show an example from this PRL in 2019, where they cooked up a model where you have corner modes, meaning that states, kind of electrons kind of localize at these states, and the symmetry here is C8, it's 8-fold rotations, and 8-fold rotations cannot be realized in a crystal. And so this 8-fold rotations kind of protect these zero modes that you see here. Then people got even more creative. They started studying fractals with finding edge states in fractals. And even now, Ade, I cannot help but mention the kind of an exciting topic that is kind of very contemporary, which is Moire superlattices, which are just two, for example, two layers of graphene with a certain twist. And this, technically speaking, for an arbitrary twist, doesn't have translational symmetry, but nonetheless, it can show very nice topological phases. So all of these are examples of phases that don't have translations, because either they have disorder or the lattice is non-crystalline, but yet they realize topological phases. However, there's kind of one type of disorder missing, as you already are imagining, which is what composes an amorphous solid, which is like lattice disorder or structural disorder, if you want. And in fact, this is kind of important because you have all these crystals that we know and love and are topological, but in fact, there are many more materials that are amorphous than crystals. And why is that? Well, first of all, if you just open kind of typical amorphous solid state books, you'll see that nearly all materials can be prepared as amorphous solids. So that's already as big as crystals, more or less, but also you can prepare them in stoichiometries that are not necessarily crystalline. So that necessarily brings the number up. And if you want to find the applications of topological phases, perhaps you want to use amorphous solids. Why is that? Because well, they have a lot of advantages, in fact, in terms of scalability and how cheap they are to grow, because you don't have to rely on like being extremely precise and making really nice crystals. But for example, if I don't know what's the average age of the crowd here, but if you're old enough to have used this type of calculators, this part here is a silicon solar cell, and it's not crystalline silicon; it's amorphous silicon. Even though crystalline silicon is much more efficient, here the calculators use amorphous silicon because it's much cheaper. And in fact, also memories use all the time amorphous materials. And so if you ever use the DVD, what you have done many, many times in your life is to pass from a crystal to an amorphous and vice versa. That's how a DVD actually stores and rewrites itself as a memory. And I'll come back to how this can help you kind of go back and forth from topological phases, actually, which is interesting because we know everything about the crystal, but kind of this side of the transformation is kind of more unknown. And why is I mean, at least in terms of the topological properties. So why are we missing amorphous solids? Maybe here's a bit of sociology of physics, but if you were like me and studied the Ashcroft-Mermin, what you will find is that, or you not find, is two things. One is amorphous solids and the other one is topological phases. By now, I think many solid state textbooks have been slowly incorporating topological phases in their chapters, but amorphous solids are, even though they're solids, they're not in solid state physics textbooks. And so that kind of lacks a little bit in our upbringing as solid state physicists or as condensed matter physicists, or of many of us. And that's kind of my explanation of why it's interesting things happen when you join these two things that people don't study so often. But why is this that we don't study that so often? There's very clear reasons. In particular, if we look from the point of view of topological insulators, I told you that we're using all the symmetries we can to find these topological insulators. But of course, if we have an amorphous systems, I just told you that these lattice symmetries are out the window. There's no crystalline lattice long range order, so this is gone, and also. Well, the symmetry labels and all the kind of momentum labels seem to be also disappearing. So how come that we can find topological insulators, and how can we find them? Well, actually, these problems have not precluded people to find topological insulators in amorphous systems. And this happened around 2017 and beginning of 2018 with these two papers and others that followed. And I'm going to explain one experiment that I think is quite nice, and it's quite smart how they came to realize this kind of quantum Hall effect analog of the in an amorphous system. So what they do is they start with a random point set, so these white dots, and now what they do is you find the area closest to any given white dot. And this procedure is called photoionization, and it actually creates, as the borders or edges of these cells kind of touch, creates a threefold coordinated lattice, which is depicted here on the right. And now imagine that at each site of this lattice, I put a gyroscope. This means just this a magnet that is rotating and has neighboring magnets that can interact. This is just a depiction of the kind of magnetic interaction expanded to second order, to just a harmonic order. So you just have to picture a magnetic interaction between the two gyroscopes, and these are allowed to kind of spin and move a little bit and wiggle around these axes. And so what you can plot is, you can kick one of these little gyroscopes and see how all the others interact. And so if they don't move, then you call that insulator. If they move, you call that metal. And so that's what they did here. They created this amorphous lattice in real life and kicked one of these, and you see that the perturbation kind of propagates only at the edge, and it has some chirality, meaning it just propagates on one direction. And they knew that could work because they had done the experiment previously on the hexagonal lattice, which is what I'm showing here, which is, well, actually much smaller, but nonetheless, you can see the edge state kind of running around as well. And so this is kind of the direct analog of an amorphous system, which means that this phase in particular doesn't really care whether you have hexagons or not, so long as you're threefold coordinated. What's harder actually is to find examples in the solid state realm. So, many other experiments followed with mostly photonic applications and scattering networks, so all metamaterials. But in the solid state, we actually only know a single material, which was kind of found by an educated guess, in the sense that we just thought, okay, well, if bismuth selenide is an amorphous, is a crystalline topological insulator, like I showed you before, maybe the amorphous form also is a topological insulator. And indeed, my experimental collaborators grew some of these. and show that instead of showing kind of completely a blurred kind of band structure in photoemission spectroscopy, you see kind of very well-defined features that are actually spin polarized, which are I'm not showing here, but this is kind of indication that something kind of non-trivial is going on. You even see repetitions of these features, which we can also understand in terms of like a scale that comes from the local order that I'll come back to a second. So basically, my group has two problems in mind in terms of amorphous topological phases. One is how do we find them? Because as I say, the one we know is basically an educated guess. And second, is the physics any different compared to crystals? So actually, for the first question, how do we find them? Well, it's actually quite hard because as I was telling you, it seems like you don't have any symmetries. And I'm not going to explain too much about this because it's quite technical, but I'm going to use a little bit of the fact that in certain models, you can still define the symmetry indicators. And the symmetry indicators, what I mean by this is eigenvalues of certain symmetries, local symmetries that still survive amorphization if you impose that your lattice is locally ordered or has fixed coordination, if you want, fixed number of neighbors. And the other thing we have done, which I also won't talk about, but if you're curious, you can ask me or check this out, is we can actually know, since we know that how to calculate all the topological properties for crystals, we can try to take a wave function from the amorphous solid and compare it to the corresponding crystal if it exists, and kind of know whether the system has transitioned into a topological phase or has remained topological. And this is something that you can do even from first principles calculations. So that's what this paper is about. However, today I think I'm going to focus more on the physical properties of amorphous systems compared to crystals. And to start, I'm just going to show you also, just to bias you a little, but also so that you know how to think about amorphous systems. Is how amorphous graphene looks. So graphene, I should remind you, is a monolayer of carbon atoms that forms an hexagonal lattice. So amorphous graphene actually looks a lot like the Death Valley. If you go to California and I definitely recommend you passing by Death Valley, which is like a national park, which is really nice. And what you will see is one of these, I think it's a Badwater Basin, I think it's called, which is basically a valley where you see all these markings on the floor. And these markings on the floor, they come from a liquid evaporating, a very thin liquid evaporating with a very uniform temperature below it. And so the remaining sediments kind of form this, in fact, Voronoi lattice. So threefold coordinated lattice. You can find even hexagons, pentagons, and squares and so on. And it's actually quite well coordinated, meaning most of the vertices are threefold coordinated. So they have three neighbors. There's obviously some defects, but this is really how kind of amorphous graphene actually looks like. If you take a snapshot, an image of amorphous graphene in transmission electron microscopy, you'll see that the local order is actually very similar to the crystal, meaning carbon is still carbon, so it will form three bonds. And if you color code it as the authors did, what you see is that you see patches of hexagons like in normal graphene, which are maybe oriented differently. And then you see pentagons in red and heptagons and other types of polygons in blue, and maybe more isolated hexagons in purple. So you have all kinds of polygons around this little patch that I highlighted here. But nonetheless, most of these carbon atoms, as they should, they're coordinated with three neighbors, because as I say, carbon-carbon bonding in the plane wants to form three neighbors. And in fact, not only that, it retains a little bit the lattice scales of the crystal. So the bond lengths, for example, are peaked at the values of the crystal. So here's the blue is the crystal and the red is the amorphous. And you see that the distribution is a bit fatter, let's say in the amorphous case, but still nonetheless peaked at the carbon-carbon distance as chemical rules kind of dictate. And in terms of bond angles, it's pretty much the same story. You have a kind of peak distribution 120, but a little bit fatter distribution for the amorphous case in red. And the last thing that I already highlighted was that there are different, there are kind of little coexistence of amorphous regions around here, and also crystalline regions. But what's interesting is that recently, actually, a very recent paper also reported that they could control, in the way they grow it, they can control the sizes of these regions of crystallinity, if you want. They can make it more amorphous or less amorphous. So amorphicity kind of goes to the right, and it will always do in my talk. So it kind of begs the question of, can we do anything with this new knob that we have? Can we induce topological phases? And so this is kind of the two things that I want to discuss. First, I'll talk a little bit about what I like to call a flat band switch. So between going from the crystalline and the amorphous, you can kind of turn on flat bands that are kind of topologically enforced in a way, or feeling enforced, actually, more to be more precise. And if I have time, I'll discuss how to go from a gapless and trivial spill liquid to a gapped chiral spill liquid as a function of disorder. So I'm going to take a little bit of water. And not sure if there are any questions. This was kind of my introduction. So if you have any questions, it's a good time to ask them. If not, I can also continue. Okay. I just continue. Perfect. I see Thomas is nodding. So perfect. So yeah. So the materials that turn between crystalline and amorphous upon applying either a light or a current pulse are called phase change materials. And as I was saying before, they're all in this optical memories. They use this technology for a very long time. And many of the materials actually use elements that are common in topological materials like germanium or tellurium. And so we thought that perhaps there was something interesting in this transitions. And so one of the things that you notice is that the pair distribution function has actually different features in the crystalline and the amorphous phases. So the pair distribution function just tells you how likely is to find the nearest neighbor from, let's say, the atom you started compared to a next nearest neighbor. And in crystalline germanium tellurium, which is one of these phase change materials, you have like essentially a central blob that maybe it's a bit skewed, but it tells you that there's basically one length scale. I mean, ideally, you'll find if this was perfectly equal R1 and R2, then you will find just a central blob. But here you find a little bit skewed. But nonetheless, essentially, compared to the amorphous, which I'll show next second, there's no what we call Peierls distortion, meaning it's equally likely to find the blue and the red at the distance similar to the red and blue. However, in the amorphous germanium tellurium, what happens is that it actually splits into two maxima. And in fact, if you let it evolve, meaning amorphous systems can actually change over time, and in this case they do, you'll find that there's an average Peierls distortion, meaning the two distances are not longer equal. And if you have ever studied any topological phase or topological course, if you've attended any topological matter course or read books about it, you'll see that this actually reminds you of a 1D example of a topological phase, which is the SSH chain. And so in the SSH chain, you have, in fact, it's a model for polyacetylene, but let's forget about that. Essentially, you have a chain with two types of atoms, and the two types are there because the distances between them are different. So you have R2, R1, R2, and this in a type bending model, you can model by two different hoppings, W and V1. And you have, if you make this W very large or this V1 very large, you have what we call two atomic limits. What we mean by this is that if I pick a unit cell and make W very large, what happens is that essentially I form a dimer that is decoupled from the rest, and the charge center sits here at the center of the bond, at center of the unit cell. However, if V1 is very large, then the charge center actually sits at the corners of the unit cell. So that's where the dimer is sitting. And so when I cut the system, it's not the same as cutting the system here or cutting the system here. And in fact, what you can show is that while you preserve inversion, you cannot deform one into the other without closing the gap. And this is kind of the condition that we say that this is, in fact, in technical terms, is an obstructed atomic limit. But loosely speaking, you can say that there's a symmetry protecting this topological phase, this topological gap. And what's interesting is that this already tells you how to do a toy model of what I was discussing before, this average parallel distortion. And this is what I'm going to describe next. So imagine you have lines that are just thrown randomly in the plane, and each line is one of these SSH chains that I was drawing here before. And now each one of these lines is an SSH chain, and they are coupled to each other by two hoppings. So one, as before, a single SSH chain has W and V1 hoppings, but you can couple them through this V2, which is this dashed line. And if you again look at the two limits, if W in this case is very weak, then you get this isolated kind of molecules with 4 sites. And indeed, if you look at the charge density, they will be isolated close to the centers of the sites. But if you take the opposite limit, you'll see that that you have something left at the boundary. And in fact, this comes from kind of cutting a bond where the charge center was sitting. And that's what this edge did. And you can say, okay, so how can we predict that this was going to happen? Since now we don't have translational invariance, it looks like we don't have symmetries at all. It turns out that kind of the model we constructed, and a type of models that we like to study a lot are these models that come from the 70s, and our contribution to this was to make them topological, essentially, which was models that were used to model amorphous silicon, meaning Byron Thorpe were trying to find why windows are transparent. So they wanted to find the simplest model that is non-crystalline, that gives you gaps, which is, if you have a gap, then it means you don't absorb light. And so at a certain frequency, and that means you will be transparent. So it turns out for amorphous silicon oxide, which is basically a window, these models are relatively good. And so what you can do is you can plot the energy spectrum. Now you don't have bands, so you cannot use K. So what you do is you plot it as a function of these two parameters. And if V is 0, so if V is strictly 0, what you have is just these W bonds, and this will just be dimers. So you will have many dimers kind of randomly oriented in space. And you know that a dimer has 2 states, a bonding and anti-bonding state. And these will be very degenerate, so much as the number of dimers in your system. And now as you tune V, you will start lifting this degeneracy, and you form these bands. So this is the gray area here. And what's interesting is that what Byron-Thorpe showed is that if you look at the envelopes of these bands, what we call the band edges, so these little dashed and these 2 dashed lines in yellow and pink, they're actually labeled by symmetry. So they keep their eigenstates, they're still symmetric with respect to inverting these 2 sites. And so if I pick a random state in one of these 2 bands, they would not have any symmetry. But it turns out these bands are still, these band edges that are colored here are still having well-defined bonding and anti-bonding character. And I told you that, we need to know basically what are the field eigenvalues of bonding and anti-bonding to know what topological state, or I need to know how these states transform under certain symmetries to know if they're topological. And so to know which states are filled, I have to know where the gaps are. And in fact, these models are sufficiently simple that you can kind of analytically solve for the gaps. And that's how Byron-Thorpe showed that basically windows were transparent in this specific model. And now we're going to do the same thing, because this is kind of like a planar version of the Weierthorpe model that I just showed. And there's a symmetry that is inversion with respect to C2, with respect to this molecule. And you can plot the density of states projected with a color that tells you how well the eigenstates match this C2 eigenvalue. So this is the plot I'm showing here. And you'll see that essentially either in one side of the, when W is equal to 0, then this molecule actually has this in fact C4 symmetry, which is colored here. So these are the even and odd eigenvalues of C4, and so you see that they're exactly an eigenstate. And what Weierthorpe predicted was that the color kind of remains well defined in the edges of these bands, which is what we see here. And so we can see that the eigenvalues kind of invert, and now the field eigenvalues kind of change. And what this means is that the symmetry eigenvalues that I was showing at the beginning for crystals here are changing, but now for an amorphous system. And what we see also is that there's like this little weight here, which is nothing but the edge states that I was showing before. So indeed, in this paper, we showed that actually not only this model, but any model that has threefold or fourfold or any fixed coordination and in any dimensions, you can symmetry label. And this kind of allows us to predict very efficiently topological phases in amorphous systems. And so we went a little bit further in 3D, and we kind of cooked up a model for germanium and tellurium, which is a little bit more complicated, and found that indeed there's a phase where when the average Pyros distortion dominates, that you have some shell of localized states at the surface of the 3D system. If you make a blob, and you cut this blob, you'll see that there are eigenstates at the surface. And if you would go and ask your ARPIS, your photo emission colleagues to measure this, you will see that essentially these states, because they're localized, they will form a set of flat bands. The reason there are many of them is because this model has multiple orbitals and multiple sites, and so this makes it such that there are several bands. But what's important here is that, in principle, by an external perturbation, be it light or a pulse of current, you could change from the crystalline, which is like a trivial semiconductor, to the amorphous phase, which has these nice flat bands. And this kind of procedure is relatively generic. You can also think, instead of, I started with SSH chains, but you could also have Kitaev models if you're interested in superconductivity, and you will get like a flat band Majoranas essentially. Okay, so I'm not sure how am I doing on time. Maybe I'll still have a few minutes to go into.
10 minutes.
Okay, good.
Minutes.
Yeah, perfect. Yeah, I think with that I will talk about the second part. So basically, so far we were looking at models that are, single particle and kind of interesting from the solid state physics point of view. Here, what we're gonna kind of switch gears and go into a slightly more involved topic, which is how to get topological states out of disorder in spin systems. So the spin systems we chose to study, this is collaboration with Cécile Rebellin, who is also in Grenoble, and the previous work, I should say, was done by the driving force was Quentin, who graduated now as a postdoc in Uppsala, and Dan Vargas, who is in the Max Planck. And so in this second part, what I want to talk about is what we call Kitaev models. So Kitaev models are this honey. I mean, there are many Kitaev models, but one of them is defined in the honeycomb lattice. And what you have to think is you place spins in each vertex, and the spins can interact. If they're in a vertical bond, they'll interact with a sigma z type of interaction. If they have the neighbor to the left, it would be sigma x, and to the right, sigma y. And this model, it turns out, it's exactly solvable, even though it looks quite, well, it's not, doesn't look like a single particle problem, but it indeed is exactly solvable. And the reason it's exactly solvable is because there are many conserved quantities, actually as many as plaquettes, and these conserved quantities are built as products of symmetry of spin matrices, and these are these W's. And because you have all these conserved quantities, you can separate the system into let's say diagonal blocks that have different eigenvalues of these plaquette operators, we call them. And the eigenvalues, because there are an even number of sigma terms, you know that the eigenvalues of an even number of sigma Pauli matrices should be plus or minus 1. And so the way to solve this model actually is not very important, but what happens is that you choose to write each spin as 4 Majoranas. This is a mapping that is allowed so long as you then kind of project back to the physical Hilbert space. And what happens is that these 3 Majoranas that have Z, X, and Y labels make up your, let's say, like kind of fluxes for a remaining Majorana, which is the central one that kind of moves and hops around the lattice. And so the let's say pink ones create a flux, which are these basically the eigenvalues of these states of these plaquette operators, and the C Majorana is going to move around. And so you know what happens when something moves around the honeycomb lattice with zero flux, which means that you just have the graphene dispersion, which is gapless. And in fact, what Kitaev showed using a theorem by Lieb is that the lowest energy ground state actually has no flux. So all these eigenvalues of these plaquettes are +1, and these Majoranas are free to move without seeing any flux, any magnetic field, let's say. And so this means that if you take, let's say, the equal values of the interactions in the X, Y, and Z directions, you'll find a gapless state that is a gapless spin liquid, because if you go back and look at what's the order in the spin, you'll see that it has no order. That's why it's a spin liquid. And now if you make one of the hoppings very large, let's say like you go from the center up here, you'll find that essentially the 2 Dirac cones that we know from graphene kind of merge and gap out. And you, as a result, you get a gapped spin liquid that has no topology whatsoever. And very shortly after this model was described, Yao and Kivelson proposed another model that looks like a relatively trivial generalization, but it actually has a new feature, which is, so they define the same exact model, except now you have triangles instead of, at every side you decorate it with a triangle. And you can still label X, Y, and Z hopping. So the only thing that you need to do that is threefold coordination. And what you can show is that because now you have triangles, the eigenvalues of these plaquette operators can be now plus or minus I, because now you have an odd number of spin of Pauli matrices. And this actually is quite interesting. It's realized also in different lattices, like this pentaheptide lattice, kind of non-Archimedean type lattice. And what this plaquette does, because of this I, actually the ground state no longer preserves time reversal symmetry as it happened in the Kitaev honeycomb model, but actually what you get is a gapped chiral spin liquid. Now you break time reversal symmetry, and what happens is that you gap out the Dirac cones that are seen by these Majoranas, and you get the chiral edge modes. This was already kind of noted even by Kitaev, that if you have odd plaquettes, you'll break time reversal symmetry. What's a recent development is that Johannes Snolle group in Munich, they kind of generalized this to an amorphous lattice, which is actually quite interesting, because I mean, maybe not kind of surprising, given the fact that you have now in the amorphous lattice, you have all types of plaquettes. So in particular, odd-sided plaquettes. And so you break time reversal symmetry. You can still color the lattice with plus and minus, find the flux configuration that kind of minimizes the energy. This is kind of the nice thing of this paper, they found the ground state configuration, the flux configuration that minimizes the energy. This you have to do numerically. And you'll find that in the local density of states, you have an edge state. Kind of forget about this white line. This is just the local density of states, which means that you have a topological state going around. And the reason you know it's going around and not just staying there is because you can compute something that is related to the Hall conductivity, or in this case, the thermal Hall conductivity, which is the local Chern marker of these Majorana fermions. And you see that it's quantized to -1 in the bulk, and kind of goes up to some very high value in the boundary. And this is kind of the typical signature. Even if you've never seen this before, you just have to think of this as some local version of the Hall conductivity, which tells you whether the system is topological or not. And in this case, it is topological. And now what's kind of interesting is do we actually have to be fully amorphous to be in this topological phase, and which is in fact the chiral spin liquid, because as I was saying, it has chiral Majorana end modes. So the way we approached this question was, okay, we're going to do again this volatilization, which for a triangular lattice, which is shown here in the white dots, means that you find the area closest to this dot, and you'll find a hexagon. Now, if you start displacing these hexagons just by a little, let's say, value of disorder, you'll generate plaquettes that are not even in the number of sides. For example, here I have pentagons and heptagons. And if you keep going, you'll find more and more, meaning by displacing just literally the original lattice and then volatilizing, you can kind of continuously control disorder. And this is kind of what I show here in a more kind of bigger system, where you have only hexagons at the beginning, and you start introducing other sides, other plaquettes with different sides. So now what I'm going to show you is a phase diagram, which goes from, in this Kitaev phase diagram, it goes from top to bottom. And in the x-axis is the density of odd plaquettes. So remember that this phase here in the upper triangle is trivial and gapped. This is gapless. And this will be here in this left edge. So what you see here is the gap, and so indeed for the value of the parameters, kind of a region of the parameters, the gap is pretty large, and then it becomes kind of gapless. But if you tune the density of odd plaquettes a little bit, you'll see that actually you have another gap which is a little bit smaller and a trivial gap, but still sizable. And if you calculate the Chern marker, or the average of the Chern marker, which is kind of this topological invariant that we were calculating before, you'll see that it's 0, like meaning trivial for this phase as we knew, but non-trivial for this other phase. And if you look at the local Chern marker, indeed this is what I'm showing here. And if I just take a cut around here, you'll see that the gap actually grows linearly with the density of odd plaquettes, and then saturates. And so the system that I was showing you before is kind of over here where the gap is saturated, but in fact, you don't need to be fully amorphous to have a sizable gap. In fact, what it looks like more is that any disorder, any number of odd sites, of odd plaquettes, sorry, will give you a steadily increasing gap. And the same you can do with the Chern marker. You can kind of look at how it grows, and basically what it looks like is that it's kind of jumping right straight from 0 to a finite value as you increase system size. And so the takeaway message here is that small density of odd plaquettes is actually enough. So if you if you take the 70%, 75% of the gap, which is it's around 30%, and this 30% is in fact the number of odd plaquettes, or the density of odd plaquettes that you see in amorphous graphene. So in realistic systems, you will be somewhere here, which is already quite enough to have a sizable gap, which is kind of nice. And we also calculated we added extra interactions like the Heisenberg term to see whether it was robust, and indeed it's as robust as the gapless state actually, which is kind of interesting. And just to show you a little bit more evidence that this really is tied to the odd plaquettes, we calculated the spin chirality, which is, if you want an order parameter for this phase that you can make local. And you'll see that for the crystal, it's essentially 0. And then as you go and increase the number of odd-sided plaquettes, you'll find that the spin chirality is essentially only peaked at those places where the odd plaquettes live. And one, I think the last thing I want to say is that one possibly maybe a little bit unrealistic, but an interesting avenue to pursue is to make a region of a let's say candidate Kitaev material, make it amorphous by just irradiating with a focused ion beam, and this you can kind of tune this chiral spin liquid phase within this region. And I think I'm going to stop here. I hope you now are free from Bloch's theorem and can live happily in a disorder system. And I'm happy to take any questions that you have. Thank you.
Yeah, thank you very much, Adolfo. It was a wonderful talk. I enjoyed it very, very much. So are there comments, questions from the audience? Eduardo, if you like, go ahead.
Yeah, thank you, Thomas. Thank you, Adolfo, for really interesting talk. Well, we are going to see if we move to the amorphous or forget about the Bloch theorem, well, according to your suggestion. But I have one question, one technical question about the local chain marker that you, I think it was in the 40, the expression for the local chain marker, because there's one Q and P letters that are
So what are the meanings? So if you remember, like if you, let's say you want to calculate the whole conductivity of a system, like a 2D system, you would sum over occupied states, right? This is what they contribute to, what the states that contribute to the whole conductivity. And so this P is just a projector to occupied states, and Q is 1 minus P, so projection to the unoccupied states.
Okay.
And, yeah, so this is very similar to the formula in momentum space, where you have also essentially a projector, which is just when you write it in the eigenbasis of the Hamiltonian, you write it in terms of these projectors essentially.
Okay, so yeah, I will try. So, and my other question is related to something previously that you showed that I think it was in the slide 36 when you explore this phase diagram of, and you show flat bands. This one. Yeah. In the panel B of the ARPES, there's something that is below the -1 and between -2 and -1. There's something that remaining.
Indeed.
There any
very good eye. So this is very generic and also very easy to explain, actually. So if in a disorder system you don't have K, right? So normally the states wouldn't have a well-defined momentum. However, imagine that your electron has very long wavelength. Then it doesn't really care what type of lattice do you have, right? So then it's propagating essentially freely, and so that what that means is that it has a parabolic dispersion, which is what you see here. And the reason it's well defined is precisely because of the fixed coordination. So all these Weierthorpe models, if you calculate the spectral function, you always find this little parabola at the bottom of the band, because it's just free electrons moving in this lattice. And since there's no, I mean, of course, if you start adding disorder, here I'm showing disorder in the sense of like on-site hopping, on-site energies that are random, or on-site or hoppings that are random, then you'll blur this guy out, like just as you would do with a normal disorder induced like blurring of a free electron. So, but yeah, indeed, it's a very good eye. I mean, every Wirethorpe model essentially shows this, and I think this was pointed out already by Thouless in the 80s. So like this was already known. I didn't know that Thouless pointed it out, but recently I found out that it was. So good eye. Yeah.
Okay, thank you. Really interesting, this phenomenon.
Thank you.
Okay,
thank you.
Okay, there are 2 questions in the chat. I will read them. In the YouTube chat, they're asking Rafael Mendes, are those amorphous materials a kind of hyper-uniform materials?
So hyper-uniform materials are a type of lattice. So hyper-uniform, I should say, so when you create a lattice, you create a point set, right? You just say, okay, my lattice points are here. And then what you could do is you can calculate the structure factor, essentially the Fourier transform of that lattice, and see what are the properties, let's say, close to gamma. And hyper-uniforms are a special type where the structure factor kind of decays as a power law as you go to the center as you go to k to 0. And in fact, so some people have studied, actually many people in photonics have studied like how hyper-uniform amorphous lattices kind of behave in terms of like photonic transmission and so on. And so so for our particular purposes, we don't necessarily care whether they're hyper-uniform or not. Actually, one feature that you can do see is that if they're hyper-uniform, they're very nicely, and they have a well-defined nearest neighbor distance, and this makes the features in the RPS kind of sharper. So that in that sense, they're nicer. But I should say that I think crystals fall on like inside the hyper-uniform criterion, because okay, maybe I'm it's on top of my head, so maybe don't quote me on that. It's good that this is live stream to the world, but maybe you can check that. But I think even crystals can be called hyper-uniform, so it's not necessarily disordered systems that are hyper-uniform.
Okay, thank you very much. Another question from Parisa Majari in the chat of Zoom. She's asking, thank you for your nice talk. Did you consider the edge ferromagnetism of these amorphous systems?
Okay, so I'm not entirely familiar with the nomenclature, but for the moment we have considered magnetic properties in this kind of K-type spin liquids. And actually, I should say that maybe I can show a plot here that these phases actually border. If you add like Heisenberg terms, they do border ferromagnetic phases that we thought could be less stable because. Well, maybe not the ferromagnetic one, but it also, like the spin liquid, kind of borders other phases like the zigzag or the stripy phase, and these are kind of translationally invariant. So we thought that perhaps the amorphous spin liquid would be actually more stable than the gapless spin liquid. And what we find, in fact, is that if we do exact diagonalization, you see like the gray line is basically the crystal, and the blue lines are the amorphous, and essentially is the same phase transition. So it's basically at the same location in terms of this Heisenberg coupling. So I'm not sure this answers your question, but so if not, please feel free to clarify what you mean by edge ferromagnetism. Maybe I'm not familiar with the terminology, but so I guess one of the short answer is no, and that these phases, one is certainly a ferromagnet, and the other one we don't know. We haven't looked. Yeah.
Okay. Larissa answers that yes, you answered the question.
Thank you.
There's another question from Santiago Galvani Garcia. Santiago, if you like, you can switch on your microphone.
Yeah, thank you. Thank you for your nice presentation. I want to ask two questions very simply. You said that there are three types, for example, the bond, the deformation, on-site deformations, and the structural deformations. Is it necessary to have these three deformations to say that it's amorphous, or you can combine two, or just have one?
Yeah, very good question. So I think traditionally, what people call amorphous solids has all three. And the reason is that normally when people studied amorphous solids, they were studying solids. And so in solids, everything happens at the same time, right? You have like structural disorder, you have like maybe some impurities that change the hoppings and the bonds. And so everything happened at the same time. Now, like as of today, you can definitely separate them. Like, for example, in synthetic systems, they can create lattices that only have structural disorder, like photonic lattices or like this gyroscope that I was saying. And so I think it's a very, very interesting question what you're asking, because the interplay between just structural disorder and disorder that has a very natural energy scale, like, you know, because when you put, like, for example, bond disorder, you choose a width of the distribution that sets an energy scale. Well, when you choose the structural disorder, it's not entirely obvious what is the energy scale that you're adding to your system. And so many phenomena that we know for that are kind of very well established in disordered phases, they have been studied for the first two types of disorder, but not structural disorder, in particular for topological phases. And so I think it's a very good question, and I think something that I definitely want to look into the future, and how they, like, only a few of these disorders kind of interplay, because now new platforms kind of allow you to kind of play with that degree of freedom as well.
Okay, thank you. And the other question is, what is the threshold between the crystalline and the amorphous systems? For example, if I put some patches of amorphous the material inside of a crystal lattices, when do you say that it is truly amorphous?
So experimentally, I think the question is actually very, very subtle. And in fact, if you have a good experimental method to determine the structure of an amorphous solid, you can certainly publish in Nature. so this means that experimentally, what typically people do is they basically do some transmission experiment, and what they see is essentially the structure factor of the lattice. And if it's amorphous, what you will see is rings, or some blurred. Actually, I might be able to show it a little bit for the amorphous graphene. Right here, and maybe even let me see if I have a better. Yeah, maybe here. Yeah, so you see, like a crystal structure has these peaks, right? These Bragg peaks, basically. That's the definition of a crystal. Well, actually, that plus the fact that it's on the symmetries that are allowed for a crystal, because quasi-crystals have Bragg peaks, but they have symmetries that are not allowed in a crystal. And amorphous systems, they just show rings. And the rings tell you something about the local distance between atoms. And if you have a polycrystal, what you would see is actually not a smooth ring, but some peaks, in fact, that so the intensity would not be uniform around the ring. And I don't think I have the diffraction pattern of a quasi crystal, of a polycrystal. But essentially, if the crystalline domains are sizable or detectable within your experimental apparatus, then you'll see this like speckles essentially in this ring. And what do you if you have different domains, you basically do an angle average, but this angle average would not be very uniform, particularly if you look locally. And so that's how people distinguish. But it's a very subtle question because because you could have nanocrystallites and those are harder to detect, and now the peaks will be like less bright and so on. So you need to kind of cross characterize in a way. Only by looking at this, you have to actually do a little bit more work to know whether it's fully amorphous or not.
Thank you.
Thanks.
Okay, thank you very much. Are there other comments, questions from the audience? So yeah, Santiago asked one of my questions about the importance of these three ingredients, on-site disorder, bond disorder, and coordinational disorder. Yeah, I don't know. Would you, from the last point, this amorphous spin liquid work which you discussed, I had the impression there that the structural disorder is the more important ingredient compared to on-site or bond disorders. Would you agree to this impression? Or?
Right. So in that particular case, it's definitely the structural disorder that drives the transition. If you would add the other two, you wouldn't break time-reversal symmetry spontaneously, and that would not get you to the chiral spin liquid phase. And so in that specific case, it's very clear that only the first two disorders would not get you there. In fact, that's been studied quite a lot. It's kind of goes back to the problem of disorder in graphene and yeah. Exactly. So indeed, you're absolutely right. Yeah.
Okay, but you said that this is true only for this particular system. This will not be.
Well, I'm not sure. I think I've lost the last part of the question.
Okay, so but do you agree that this is only true for this particular system, or will it be a necessary ingredient, let's say, also for other systems? Or
so that's a good question. So in this particular system is important because you care about odd loops versus even loops. And presumably you can cook up other models where you care about like the connectivity of the lattice. I think one interesting thing about this structural disorder is also in terms of how you localize states. So for example, if you're interested in flat bands and making things like quenching the kinetic energy for some reason, then perhaps there are ways of finding whether you have localized states, exact localized states in a system, and that's like going back to you can map it to a problem of putting dimers that are frustrated or not, meaning you put some dimers that have not to touch, and if they touch, it means that you have if you go back to the electronic problem, you'll have a localized state. And this has been worked out by Felix Flicker in quasicrystals, for example. And one thing that you find is that some quasicrystals allow for perfect matching, and others don't. And the ones that don't have a flat band. And so I think, and so they could explain the origin of, for example, flat bands in perimeter stylings by this dimer construction. And I think doing this dimer, I mean, it's probably not analytical, but it's also interesting. Let's say if you add like certain defects or not others, then you might be able to kind of play around with this degree of freedom. So yeah, indeed, that's Yeah. I think it's, generically, I would say that maybe all disorders can do similar things, but for specific systems, you might find different phenomenology for different disorders. Yeah.
Okay. Okay. Thank you. I have another rather detailed question on page 34 of your presentation. You showed these bonding and anti-bonding bands.
Yeah.
And can you explain me the asymmetry of the size of the band 1 and band 2? So why is band 2 much larger than band 1?
Let's see. Is this a sketch or does it have to be like that?
Okay.
I have to think. But I think you're right that I think you're right that basically the bandwidth is V essentially, right? So they spread as much as V lets them. And so both of them should spread around V, and they should be the same. And in fact, I think that I think you're right. Yeah, they should be. I was just thinking whether. So one thing that can change is so depending on the lattice, you might have. Well, actually, you actually see it here that essentially the width is similar as you depart. So now I was going to say that maybe there's some, like, depending on the lattice, there might be localized states. Like, for example, in the honeycomb lattice, you can, if you make a pentagon, you can localize a mode, maybe algebraically, but you can more or less localize a mode, and that will sit somewhere inside the gap. If you open a gap, it will sit somewhere inside the gap, and so this could be closer to one band than another, and then they will create an asymmetry. But this is not the case in this model, though.
Okay.
But I think generically, I think what I'm saying is that you might get states that are kind of in the gap in some models, but I think you're right that this should be. Maybe I will update the plot and make them equal.
Okay.
But a great remark as well. Like a very, I've given this talk many times and nobody has told me that. So it's a great observation.
Okay. Yeah.
I'll use this figure at least. Yeah.
Okay. If there are no other questions from the audience, again, Adolfo, thank you very much for this wonderful talk. I enjoyed it very much.
My pleasure.
Thank you very much for working late night for us. I think it's past 10 in France, and I'm asking this nasty question.
No, it's perfectly fine.
So
yeah.
I apologize for this. And again, thank you very much, and hope to see you soon in person.
Yeah, let's keep in touch. I would love to visit sometime in person. Yeah, thank you for the invitation, and it was a pleasure to discuss. Yeah, thank you.
Okay, thank you. Bye. See you next week.
Bye.